Hello everyone, my name is Viraj and today we'll be discussing the sixth problem from the CP-31 sheet by TLE Eliminators under the 800 rated questions. Let's go. So I'll be moving on to my CP-31 sheet over here. I have the 800 rated parameter ticked off and I'll be moving on to my sixth problem, Doremy's paint 3. Let's read it. So an array b1 to bn of positive integers is good if sum of two adjacent elements are equal to the same value. More formally, the array is good if there exists a k such that b1 plus b2 equals to b2 plus b3 equals to so on bn minus 1 plus bn equals to some integer k. Now you have an array A of length n. You can permute its element, that is change its order however you want or however Doremy wants, and determine if you can or Doremy can make this array good or not. If you can, you have to print a yes, else you print a no. Alright, so let's try to generalize the problem and understand what are they asking over here. So they have of course given you an array. Alright, they have given you an array over here. This array is called A. And in this array A, I have the numbers A1, A2, A3, A4, so on till AN. So I have an n sized array. You can call this n variable that is given, that's the n sized array. Now effectively what do I want is, I want that every two pair of adjacent elements, that is if you take these two numbers, these two numbers, these two numbers, these two numbers, so on, that is A1 plus A2, sum of two adjacent elements, A2 plus A3, A3 plus A4, so on, you can write the last element to be AN minus 1 plus AN. You want an equality among them. You want that these set of pair of numbers with giving a sum, that is adjacent elements being summed together, is actually a same value. They have called that value as k. Now the condition is that this is not given, like the array is not initially set in such a way that this occurs. The actual problem is, given that you have been allotted this array with some a1 to an numbers, can you reorder the elements such that the condition becomes true? Okay, becomes true. This is the question. So given that you have these elements a1 to an, you want to somehow reorder them. Alright, never in the question it's written, by the way, that how much operations do you want to reorder, what are you swapping. That's not the problem. Just simply asking, very important point to know by the way, whether a yes or no gets printed to this question, that if I would have given you the power to reorder the elements however you want, can you fulfill this condition or not? That is, somehow the adjacent elements have equal sum. Okay, great. So I think you have understood the problem. It's a very, very basic problem when it comes to understanding what condition are they asking. Just draw this on pen and paper and you will understand, okay, I just want adjacent element sums to be equal. Now, considering that this part is done, let's actually go back to some test case and understand that what are we essentially looking for. Alright, so let's say I have a test case, that looks like this. Okay, 1, 1, 2. So I'll take this test case. I have the array equals to 1, 1 and 2. Now a very simple reordering in this that can be done is, you can reorder it to look something like this: 1, 2, 1. Simply, I'm not bothered with how much operations did I take to reorder or what numbers do I swapped from which place to which place. It's just that somehow the array that was 1, 1, 2 now looks like 1, 2, 1, which is of course a reordering. This is of course a reordering of the elements. I have brought my 2 to a location where I wanted to keep it, and it's helping me. Why? Because now if I took up adjacent elements sum, this is 3 and this adjacent elements is also 3. So isn't this same? Of course this is same. That's why this reordering is possible and your answer becomes yes. Alright, so I hope the problem is clear, the sample case is clear. If you pick up your pen and paper, you will actually see that what's the meaning behind the other cases also, and you will realize, okay, this is when the answer is no, this is when the answer is yes, in the explanation for these test cases. Alright, so very, very simple problem to observe and simple problem to picturize the condition for. Now comes the main part. How do we actually begin with the problem? Or to be very specific, even before beginning with the problem, do I want to discuss some ideas which might help me create a picture that, okay, this might work, this might not work. What do I mean by this is, do I want to discuss the expected time complexity? And the answer is yes. Because if let's say by fact, I have some things with me, in 1 second I am allowed 10 power 8 elementary operations. And if I look over here in the problem, time limit per test is 1 second. So if I talk about one test, how much Codeforces is allowing you to run the problem in? It's basically allowing you 1 second, which means effectively 10 power 8 operations. But now, one thing to observe is, in every test, there are some test cases. So you can see the input is going to consist of multiple test cases. That means each test has some test cases, and those test cases are actually in 100 order. So if my question changes and I ask you, what's the number of elementary operations you perform for each and every test case, then your answer is 10 power 8 upon 10 power 2, that's the maximum per test, and you write this as 10 power 6 elementary operations. Now this is very important because if I look at n over here, which of course is assumed to be my expected time complexity's main dependent factor, then n being in 100 tells me that I can create a solution in a boundary of n cube. Can I create a solution that looks like n power 4? No, because n power 4 means basically I'm going in 100 power 4, that's basically 10 power 8 by mathematics, and 10 power 8 is of course greater than 10 power 6. But if I talk about 100 for n cube, will that work? Of course that works, because this creates a 10 power 6 solution, and this is good to go. And if this works, anything below this, O of n square, so on, even if you create a constant solution, all of this definitely works for you. And now you have an understanding that, okay, this is my sort of an upper bound. I don't want anything that looks in this order, but anything below this is good to go. Now this is my discussion for expected time complexity, and this is very important because if I now have a clearer picture of what time complexities do I want to achieve, I might not think of any idea which runs in a higher time complexity, because pre-hand I know this is TLE and this might be accepted solution. Alright, great. Now we can actually begin with our main idea of the problem. Alright, so the main idea of the problem starts with first understanding, is the problem more simplified, or to be very specific, can I simplify the problem even more? Alright, let's look over here. Let's understand what are they asking actually. If you have a general outlook, it's basically A1 plus A2 equals to A2, like this is A2 plus A3 equals to A3 plus A4, so on. So if I ask anyone that, can I generalize this bit, right? I would just want to generalize this whole mathematical notation. It's basically saying that, okay, if let's say I have a number AI, I have the number that's actually behind that, addition of this is actually equal to that number plus the number after it. That's AI plus 1. Is this correct? Yes, because this fits for every condition, right? If let's say you have I equals to 2, you're basically getting A2, A1 sums equals to A2 plus A3. That's the next. So this condition is actually true for all indices belonging from 2 to n minus 1. Now, why have I generalized this? Because this is a very important observation that right now, if you observe the general sum, can you say that this term and this term is cancelable? Of course, right? Because A1, and if let's say if a simple mathematical equation is asked to you and I write the same terms on both sides of equality, you can cancel them out. So AI and AI are basically cancelable. That effectively means you are talking about the previous number being equal to the greater number when it comes to some ith index. That is, if I talk about A of I minus 1 and A of I plus 1, then I have a difference of one index in them. So basically, if I have this A1, A2, A3, A4, A5, so on till AN, then what do I essentially want? If A1 comes into picture, essentially A1 has to be equal to A3, has to be equal to A5, has to be equal to ... so on. That is, every two numbers, or every, you can say, jumped two numbers, two difference, so on, have to be equal. On the other hand, same thing, A2 has to be equal to A4, has to be equal to A6, and so on. And this is a very crude observation and very important observation in this problem. Alright, let's go one more time. What I've done is I generalized my main condition into a simplified mathematical notation where I knew I was belonging from 2 to n minus 1. Then I had a very clean observation. If I have two terms that are on the same side of equality, they can cancel out. So a of I minus 1 is effectively equal to a of I plus 1, which means effectively for an ith index, you are jumping to two places. So if I talk about A1 has to be equivalent to A3, has to be equivalent to A5, will be equivalent to A7, A9, A11, whatever comes in my boundary, and A2 has to be equivalent to A4, has to be equivalent to so on, so on, so on. This is what is going to happen. Alright, I hope this has become clear. Now, once this idea is clear, I hope pretty much the problem is very, very simple to understand. Because essentially what are you saying? You are saying that odd index positions and even index positions. These two positions should have the same numbers. So effectively I'm talking about both these conditions separately. Odd index positions should have numbers which are same. So I can say this, same numbers. And even index should also have same numbers. If I'm able to reorder the array in such a way such that I find same numbers kept at the odd indexes and same number kept at the even indexes, then will I not for guarantee say that A1 is equal to A3 is equal to A5, that means odd indexes are same, and A2 is equal to A4 equals to A6 equals to A8, so on, even indexes are same. And will that not create the array to be good? Of course that creates my array to be good, because I have fulfilled the condition effectively of being every two adjacent sums being equal and effectively being equal to some main variable k. Alright, so this is the whole problem. Now we have a better idea. All we effectively want is same numbers in odd and same numbers in even. Now how do we check this? What is the piece of code that is going to help us? Now this is, by the way, an implementation detail, right? We get the idea. You can of course implement it by pausing the video on your own, but let's go ahead and discuss how do I smartly implement it and what do I effectively want to check. So understanding this is very important, that very clearly my answer is no in a scenario when I have more than or equal to 3 distinct integers in my array. This is a very clear case of no. Why? Because understand this, if let's say you have 3 separately distinct integers, what can happen is you chose, if let's say you give a number the position or the power to occupy all the odd index positions, and then you give some other number the power to, let's say I'll call this number 1 n1 and I'll call this number 2 n2. You give some other number n2 the power to occupy the even index positions. Then can some other distinct n3 number even exist? No, right? Because you only had 2 same number cases. Some same numbers have to be fallen on the odd index positions and some same numbers need to fall on the even place conditions. So there is no viable choice with some extra number n3 or more. Where would you have kept it? No position left, right? That means if I have some array which has more than equal to 3 distinct integers initially only, then the answer is always no, because I cannot create any reordering. To create any reordering, I want less than equal to 2 distinct integers in my case. Now I'm not saying for sure, but this is what I effectively want. Alright, I hope this should be clear. Now let's move on. If the no case is clear, I'll just give you a quick example also, by the way, for this. If let's say the array looks something like this, 1, 1, 2, 3. Then if let's say you just place at even odd positions, this is 1, this is 1. And then in even index positions, you place this 2, and then the other number might be 3. So although your odd index positions are good to go, but your even index positions are becoming a problem, because now you have separate integers, right? That doesn't make sense. Either this would have been a 2, then you were good to go. Or this would have been, let's say both would have been a 3, then also you were good to go. But having 3 or more than 3 distinct integers is definitely a problem. So I hope this should be very clear, right? You can pause the video, check this with your pen and paper on theory, create some cases, and you will get the no part very clearly. Alright, now let's move on to some other casework of when is my answer yes, and do I still have the possibility of getting an answer no? Let's see. So over here, idea is clear. I am only now talking about cases where I have less than equal to 2 distinct integers. So I'll take an example. we have the first case that I'll say, okay, I had a number n1 and I had a number n2. These, I'm taking the case where I have two distinct integers in the array. Now, what do I essentially want to do? If let's say you have this array and let's say you have, let's say 6 positions, 1, 2, 3, 4, 5, 6. Then effectively what do you want? You want that, okay, n1 falls at this place, and this place. And let's say n2 falls at this place, and this place. Now this is an sized array 6, by the way. Let's take one more example for a better understanding. I will have, let's say, 7 positions. So this is 1, 2, 3, 4, 5, 6, 7. Now what do I want? I want something that looks like this. Maybe I have n1, 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 n1 over here. And maybe I have n2, n2, n2 over here. Or in the same scenario, I can have something like this also, by the way. Maybe I can have, if I have 7 positions, 4, 5, 6, 7. Then if this is the 7 based case, this is for n equals to 6, this is for n equals to 7. Then I can have one more case where I keep n1, sorry, not n1, n2 at this location, n2, 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 and n2. And how about I keep n1 over here, n1 over here, n1 over here. So tell me, are these two cases giving you the correct answer? Yes, because if I talk about this one case, then you have basically an n equals to 6 array. And what you did was you effectively kept n1 at the odd positions and n2 at the even positions. And let's say you have something like n equals to 7, then there can be two cases where you kept either n1 at the odd positions or you kept n1 at the even positions. Now try to understand why I have drawn this diagram. First diagram is being very clear to tell me a quick observation that if let's say the frequency of n1 is f1 and the frequency of n2 is f2, then if f1 is equal to f2, you are good to go. You can print your answer to be yes, because very simply, if your frequencies of the two distinct numbers match, then you can just place effectively half of the numbers at odd locations and half of the numbers at the even locations. This is what I did over here. But the issue is, isn't this only possible for an even-sized array? Effectively, yes, this is only possible for an even-sized array. Because for an even-sized array, you will have n by 2 positions to be occupied by the frequency f1 and n by 2 positions to be occupied by the frequency f2. But if let's say I talk about the case where n was odd, that is why I actually took this case, by the way, right? Where if let's say your n is odd sized array, then you have sort of two ways to do this. It's not necessary that the frequency, or in this case, it's not even there that the frequencies have to be same. To be very honest, the condition has to be that the absolute difference between f1 and f2 should be less than equal to, or sorry, not less than equal to, should be effectively equal to 1. Should be effectively equal to 1. Now, why is this true? If let's say the frequencies absolute difference is equal to 1, then you know for short that basically one frequency, any one of them, maybe f1, maybe f2, I'm not saying right now because I took absolute, any one of the frequencies is greater than the other frequency by just one position. So if let's say assuming, let's say n1's frequency was greater than n2's frequency by 1, I could have kept n1 at the odd locations. So odd, 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 odd. 4 locations at total. And n2 at the even locations, even, even, even. So basically 3 locations. Can I say 4 is greater than equal to 3? 4 is greater than 3 to be specific by only one difference. Yes. And counteract to this case, if let's say n1 had a frequency that's actually less than n2 by only 1, that is f2 is let's say 4, and like this, the case is swapped basically. You can say you have a 3-4 frequency. Then you can just create a case that looks like this. You place n2 basically at the odd positions and then you place n1 at the even locations. In all these specific cases, you start getting an answer yes. And the argument is, besides this, any such case, specifically when it comes to this absolute part, is kind of going to give you an answer no. Alright, so we'll come to that part. Let's just follow up to our next query. So what I did over here is, this was part 1. Effectively what this was, we said no for 3 distinct integers. Okay, this was for 3 distinct integers. Now I'm saying I'm going to take 2 distinct integers. This was the case. This is 2 distinct integers. Now I'll take my final case where I say I have only 1 distinct integer. So basically I'm going to not write this. I can just simply say I have a single number n1 that encaptures the whole array. Now this is a very simple case. If I have n1, that's the single number in the array and it's only occurring in the array, it's capturing the array fully, then do you have to make such cases? Doesn't make sense, right? If let's say this is n1, just place n1, 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 n1 everywhere, and you will of course have, let's say n1, 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 n1 everywhere, and you will of course have the odd positions and the even positions to have a same number, because actually the array had same number only in the whole part. So case number 2 is actually very simple. Maybe I could have discussed this even earlier, but then it's fine. It's basically a case number 2 is actually a direct yes, but case number 1 is a problem at some specific locations. Let's try to identify that part. You have a yes, of course, when you get same frequencies. Good to go. N by 2 size. Just fit it up. But what about this absolute f1 minus f2? This is giving you yes. Now let's take a case over here. If you did not had the absolute frequency to be equal to 1, maybe you had, so this is absolute frequency equal to 0, that's the first case, or basically equal frequencies. If you have the absolute frequency greater than 1, then what can happen is, will you ever get this condition to be true? Will you ever get this second case to be true for n equals to 7, for example? No, because what will happen is, let's take an example. Ideally, what can happen? Maybe n1 was coming 3 times and n2 was coming, let's say, 5 times. Now, what's the problem in this? See over here that if n1 is coming 3 times, okay, I have 3 times coming over here, n1, and maybe I could have done something like this. Not this gives me a net frequency to go above 7. Maybe this is n1. This comes 2 times, and then I can have n2 that is coming 5 times. Or this is a better case. Now try to understand this. n1 is going to be kept at the locations that it wanted to be kept, but then n2 is exceeding the limit, because if n1 is kept at the odd location, even location, then this n1 position that should actually have been there is no longer with you, because n2 hasn't captured it, and now you will have to be forced to keep n2 over here. So effectively, it means if I have an odd sized array, I do want to keep n by 2 elements and n by 2 plus 1 elements, or having the difference to be exactly equal to 1. If that hampers my situation, then I will actually want to report a no. Alright, so this is the mixed bifurcation of all the cases. Now what you can do is you can pause the video, try to understand what we discussed. Again, I'll revise the solution once more. You are definitely printing a no when you find more than 3 distinct integers. Good to go in this part. Next, we can take maybe second case first. If you have the array having same numbers throughout, directly print a yes, again a I blind situation, because you know effectively always odd and even positions will have same numbers. Whole problem rises what happens when you have 2 distinct integers, and then we have some cases. We say, okay, if the frequency is f1 and f2, if both frequencies are same, then good to go, because I know in that case what I can do is effectively I can print up the numbers to have in such a case order. N1 is equal to N1 at odd positions, N2 at even positions, or N2 at even positions, N2 at odd positions. Effectively, it doesn't matter. But if let's say I have the frequencies of F1 and F2 not equal, then the next yes case is only existing when their frequencies have an absolute difference to be 1. If that doesn't happen, you directly print a no, because if their frequencies don't have an absolute difference equal to 1, you will never be able to somehow manipulate them to fit odd and even positions equally in an even manner, so that odd positions have the same numbers and even positions also have the same numbers, which was effectively what our condition that we discussed initially. We want A1, A3, A5, so on numbers to have same thing, A2, A4, A6, so on numbers to have same thing. So this idea actually comes from the observation that, okay, I was able to identify even and odd positions, and this is when I bifurcated my whole situation. Alright, if you are able to picture the case working in what happens when you have odd sized array, what happens in even sized array, then this idea of having equal frequency and absolute frequency difference equal to absolute of the frequencies to be equal to 1 becomes very, very clear. Alright, so this is all that we had to discuss in the problem. Now, we can actually look at to our code part and understand how do we implement this out using maps. So this is a very important concept that falls for beginners also. How do we present maps in this case? Alright, let's look over here. So what I will do effectively is I'll take the input of the test case t, then I have the input of the variable n, I have input of the array. So all I'm doing up till over here is simply taking the inputs that were given to me. Now I have something interesting. I have a map That's the frequency map, of course. I'm using a frequency map because it's much easier to maintain frequencies. And all I'll do is first I'll create my map. I'll just push or insert AI numbers plus plus. That's basically creating frequencies of every number in the given array. Now what do I want? Very simple check. If the frequencies map's size goes greater than equal to 3, isn't this my initial case that we discussed? That was the no case. Yes, that's the no case. I do want to print a no directly if I feel the size is greater than equal to 3, because that means I have more than equal to 3 distinct integers. But if that doesn't happen, what do I want? I know for sure that the frequency map will either have only one element or it has two elements. So to extract them, how do I extract their frequencies? This is the way of writing. This is one of the ways of writing. Again, an implementation difference. Maybe you can call it another way. You will find some other pieces of code you can explore. This is how we implement, or we propose to implement. Begin iterator is the first place where the map points to from the start. And our begin actually is the iterator, which is the reverse of the begin, which points from the end. So I'll just define it over here only. Begin is the iterator that is from the start. That's the first element. And our begin is iterator. That's the last element in the map. And in that, if I call this arrow function, which is basically calling that iterator's property, second, that means the frequency, effectively what do I get is, I get the first frequency, that's F1 we talked about in our question over here. Over here we talked about F1. And once I say if R begins second element, that's basically F2. So what I've done over here is, by very simple implementation technique in the C++ language, I have extracted the F1 and F2 given in my current array. Now, very simple case working as we discussed. If F1 and F2 are same, this of course means you have most probably an even sized array. You have same frequencies, just place any F1 elements in odd positions and any other F2 elements in even positions. Great, good to go. But what is an else if case? Else if case is, if you have an odd sized array and you feel that the absolute frequency of the two numbers are equal to 1, then that means great, good to go. I can of course consider it to be a yes case also. Else I will finally print a no. Now your question would be, this implementation technique might not be considering the point number 2, where I said all numbers are same. But the argument is, it is. Why? Because if you look over here, you are basically getting the frequency of the first element from the front end and the R begin, or the reverse elements from the reverse end. Now this technique is helping me do one very important thing. Let's say that the frequency map has only one element. That is effectively your case 2, where every element is same. Then aren't these both frequencies going to point towards the same value? Of course, right? If let's say you have 5 same elements in the array and 5 is the size of the array, F1 will also be 5 and F2 will also be 5. So where do you check to print yes? Of course in this condition, right? Where F1 is equal to F2. So we have smartly in our code also added up our case number 2, where we did not have to create a separate check where we feel, okay, was the size of the frequency equal to 1? I could have actually kept a check over here also, right? But that would have unnecessarily increased my if and else checks, right? So all about CP, all about simple tricks that I wanted to talk to you about in this problem. And this is the whole idea. Effectively understanding that all we had to discuss was same number frequencies are odd and even was the main crux of the problem. All we discussed right now was how effectively can we implement it, how do we realize there is something known as a begin iterator, there is something known as a reverse begin iterator, and it's helping us gather the facts that what was frequency 1 in the map and what was frequency 2 in the map. Alright, so a very fun problem. Let us quickly discuss the time complexity now. Since I'm discussing over here, or I'm taking into consideration a simple map, this is an ordered map you can say, or a simple map, you have a log in frequency for insertion and deletions and searching also in this map. That means if I have an n complexity over here for simple taking loop, I will have an n complexity over here for iterating to every element, but insertion will give me log n over here also, which effectively means that this whole insertion in the map is n log n, which is n log n. This is not simply O of n. This is again a very beginner mistake you can create when you don't understand the frequency, the complexity behind utilizing a map. So effectively your time complexity right now is n log n. Then you have simple check over here, not a big deal. And then simple checks over here also, very simple constant checks. That means my actual complexity that I'm receiving right now is not n order, which might have been the very first look at the problem. It's actually n log n. So if I write this over here, this is n log n, or to be specific, log base 2n. This is what we more prefer to write. And now if I talk about n being 100 order, what means is if I calculate O of 100 into, you can say, log base 2 of 100. You somewhere get a complexity or a number of operations. So log base 2 of 100 is effectively somewhere around 7. So you get O of 700 or 700 elementary operations approximately. Now, isn't this very great? Because we wanted a complexity that can reach a boundary of 10 power 6, and we have created a solution that runs in 700 elementary operations for each and every test case. So this is definitely going to work. My logic is right, fetches me an accepted solution. And what about the space? Space is not dependent on any log n factor. It's basically dependent on two things. One, you have the frequency map with you, and you have the initial array where you're taking the input. So array is of course having an n size, and the frequency map also might exceed to an n size, considering maybe you have many unique elements. So maximum order of your frequency map plus your array can be written as n plus n, which effectively means 2n, which is basically O of n, which means O of 100. That's the n order. So space is good to go, TC is good to go, time is good to go. That means gets me an accepted solution is going to work. Right. So all we had to observe was this idea of odd and even indexes. Then this is sort of a very implementation heavy problem for a beginner point of view, but it's very informative problem if it comes to realizing how is the concept of iterators important when it comes to maps, and how do I manipulate different techniques in frequency maps to be very specific to get answers quickly. And one of this was this trick of begin and rbegin. That is something that I'm telling you in this problem. You can of course take this problem to be solved in some other implementation also, not a big issue. Okay, so I hope you like the video. Thank you for watching.